Okay, so today is going to be about infrared spectroscopy. So we talked so far about UV vis absorption. We talked about fluorescence, phosphorescence, and microscopy. So today is about infrared. And so remember those vibronic states that we said, okay, we don't really care because we only care about the lowest excited state, Kasha's rule, etc. Well, in infrared, actually, we do care. So we're going to look at vibrations. Okay, so infrared, red spectroscopy, IR. Okay, so IR. So first, a couple of small statements. So IR looks at vibrations, and they are between the visible, right, and microwave regime. So it's from 4,000 till 400 inverse centimeters. So this is wave number. We'll get back to what that exactly means. So you see that each field of spectroscopy uses their own units, which is seems weird, but it makes sense. It will make sense later. Okay, 0.5. So if we convert this to to electron volts, it's 0.5 to 0.05 electron volts. So remember if you look at electronic transitions, it's more in several electron volts. So we are an order of magnitude higher lower in energy here as compared to UV vis. There's also two other, we're not going to talk about it. There's a field which is called near infrared. That's 14,290 to 4,000. And there's also something called far infrared. Okay, 700 to 200 centimeter minus 1. And so why do people distinguish between those regimes? Because the machine you need to do near infrared and far infrared is different from the standard machine you use for infrared in the lab. It's just a practical thing. There's no real, well, there's some other reasons, but we won't go into that. Okay, so compounds, they have a unique spectrum. So you can use it to characterize compounds. If you have a pure compound, you take an IR, you compare it to a database that stores IR spectra, you can identify compounds, except enantiomers. So because we're looking at vibrations, chiral centers don't really matter, right? So we cannot distinguish enantiomers. And within compounds, there are often what's called characteristic bands. So it's usually functional groups, let's say an acid or a ketone, that have a characteristic wave number, and you can identify them using IR in your spectrum. The downside of infrared is that it's very complex to interpret. Okay. So you have to use it together with other techniques. So if I just give you an infrared spectrum, it's not like NMR. If you are good at NMR, I give you an NMR spectrum, you might be able to say which compound it is. But you might, in infrared, you definitely need something like the mass spectrometry. or NMR. So this will be in the next classes, we'll go into that. And then we'll see how to combine all of these things together, okay? So infrared bands, they are shown in wave numbers. So this is nu bar. Okay, the units are centimeter minus 1. So you say nu, like the Greek letter, and bar is the horizontal stripe over the nu. So it's not to be confused with nu, which is the wave, or lambda, which is wavelength, or the frequency nu. But they are all related, right? So if we look at wave number, nu bar, this is 1 over wavelength. Okay, so for example, 1 centimeter to the minus 1 is 10 to the 7th nanometer. Okay, this is just, so in UV vis, it makes more sense to use wavelengths, and in infrared, it makes more sense to use wave numbers. And why? Because some of the bands, so the scaling is an inverse proportional scaling. So the bands are more, like narrower and easier to identify in wave numbers than they would be in wavelengths. Okay, and so frequency is the speed of light over the wavelength. Okay, light. So for example, 400 nanometers wavelength would be 7.49 10 to the 14th hertz. Okay, so those are the units. And then, so infrared bands, they are usually shown in transmittance. T, right? But can also be absorbance. A. Okay. And so for UV vis, they often show transmittance expressed in percentage, right? So 0% transmitted means everything is absorbed. Okay, so usually on the y-axis of an IR spectrum, you will see percentage of transmittance. If you talk to organic chemists, they will just say an absorption can be strong, it can be medium, or it can be weak. Okay, this makes sense. So that's usually how, when people write down vibrations, they also note like S, M, or W for strong, medium, or weak for the vibration. Okay, so what do you see with infrared? You're looking at vibrations, not electronic transitions. Okay, so this is very different than UV vis. Okay, so we're looking at vibrations, but not all vibrations are visible in infrared. Okay, so infrared looks at a change in the dipole moment of the bond or the molecule you're looking at. So if you look at homonuclear compound, for example, hydrogen. Hydrogen has two hydrogens. If I look at the change in this bond length, so let's say I'm going to stretch the hydrogen bond, then I don't have any change in the dipole moment. So this means no IR. So they say it's inactive IR band. You don't see it in your spectrum. If I have heteronuclear, for example, I have a hydrogen carbon bond. So carbon is much larger, it's electronically different, so you have a small dipole moment. And if I change the length of this band, right, then I change the dipole moment. So this will be active in infrared, right? So you have to imagine that I'm going to stretch this bond, and therefore I'm going to change the dipole moment of this compound. So that's the first thing you have to look at. Do you change the dipole moment? If not, you won't have any IR. If it is, then you will see it in IR. Okay, so there are different ways to try to understand what we measure and why we get any signals. And the first one is understanding from a viewpoint of classical Newtonian mechanics. So what's classical mechanics? Who can explain me? Classical mechanics, Newtonian mechanics. What is it based on? So usually, let's say you have a force which is proportional to a displacement times some kind of constant, right? This is like if you kick a ball, it will fly away. This is like let's say high school physics is Newtonian mechanics, right? And so if we use that viewpoint first, and we look at a single vibration, right? So a vibration between two different atoms with mass m1 and m2. Okay, so we're going to look basically at a little weight with a spring in between, right? So we have m1, m2. So really think of two weights with a mechanical spring between them that are floating in space, right? So they're not attached to anything except for each other. And so they will have some kind of equilibrium distance that I will call R equilibrium. And so if we stretch these two weights, okay, so the spring will be stretched, I have some kind of maximum distance, R max. If I compress the spring, so this is all reversible, right? Then I have my spring compressed, and there will be a minimal distance. Okay, so that's nice. How can we use this? So we can express the energy of this vibration as follows. So the energy of vibration is the potential energy plus the kinetic energy. All right, okay, so let's write this down. Potential energy, EP, and kinetic energy. Okay, so this is the same as if you have you have a weight and you lift it up, it has a high potential energy, but no kinetic energy. If you release it, potential energy is converted to kinetic energy. High school physics. Okay, same thing here. So we have the potential energy is half times K times R minus R equilibrium squared. So this is, again, this is just Newtonian mechanics. So this K is the force constant. This is basically how stiff is this spring. So if you have a stiffer spring, K is higher. If you have a weaker spring, then K is lower. And this is the difference. This says the actual position of R as a function or as compared to the equilibrium distance. Okay, so if you look at this equation, if the position of the two weights is equal to the equilibrium distance, then this term is 0, right? Then potential energy is 0. So we can look at different positions. So if we look, if the position is R max, then the kinetic energy is 0, right? So if you stretch the spring all the way, it cannot move more. So the kinetic energy is 0. And therefore, the vibrational energy is half times K R max minus R equilibrium squared. Okay, we can do the same thing at the minimum. So we say at R minimum. Again, kinetic energy is 0 because you cannot compress the spring more. So all the energy is potential energy. So that means the vibrational energy is equal to the potential energy, this one, right? At the minimum, so half times K R minimum minus R equilibrium squared. Okay, so it could be helpful to look at this in a little graph. So we're going to plot vibrational energy versus R. And we have in the middle the equilibrium distance. We have the maximum distance and we have the minimum distance. Okay, so in this case, we'll go up somewhere. The total vibrational energy is constant, right? Because I have potential energy, I have kinetic energy, but the total vibrational energy is constant. But I have these two contributions. One is kinetic. Oops. E kinetic. And the other one is potential. Okay, so this is how we can think of vibrations. And staying in this Newtonian mechanics, we can actually transform this directly to wave numbers. So this is based on Hooke's law, which was made for springs, but it applies also for infrared. So we're going to look. So I'll just try. Okay, so when I draw this, when I put zeros, I put a little stripe through it to make sure it's a 0 and not an O. Okay, so it's V0. or nu bar 0, sorry, is 1 over 2 times pi times the speed of light times the square root of k over mu. Okay, so what is all these things, right? So nu bar naught is the wave number in centimeters minus 1. C is the speed of light. But pay attention because the units are centimeter per second. So normally the speed of light is 3 times 10 to the 8 meter per second. So, but since we're going to use centimeters, inverse centimeters, we're going to write everything in centimeters. Okay, so again, like always, be careful of the units. This is the force constant. And this has also funny units, dyne per centimeter. Okay, we'll see what that is. And then we have mu. That's the reduced mass. You might have seen that somewhere. So m1 times m2 over m1 plus m2. Reduced mass has no units, okay, dimensionless. But you have to, so the weight, you have to calculate it in grams, right? So you take the weight of, for example, the atoms, you calculate the reduced mass based on the, how many grams is each atom. So this dyne, 1 dyne, is 10 to the minus 5 Newton, or it's 1 gram times centimeter over second squared. Okay, so again, this K is proportional. Let's write it to the stiffness of the bond. Okay, so for a single bond, for example, carbon-carbon, it's roughly 5×10 to the 5th dyne per centimeter.
Sorry?
Yeah.
For the reduced mass, it's mass square and mass. So I think it's mass for the unit.
Right. It is actually, that's true. Yeah, that's true actually. Yeah, very good. Yeah, so it's true, right? It's gram squared over gram. So it becomes gram, right? And that makes sense because if you look at the dyne, right, the force constant, it has gram also here. Okay, thank you. Yes, you're absolutely right. Okay, so reduced mass is in grams. Okay, sorry about that. So the double bond is roughly 2 times that, so 10 to the 6th dyne per centimeter. And the triple bond, 1.5 10 to the 6th. So, oops, 3 times as strong. Okay, so let's look at an example. For example, carbon, hydrogen, right? So the mass of carbon in grams is 1.9943, 10 to the minus 23 grams. And the mass of hydrogen is 1.6735, 10 to the minus 24 grams. And it's a single bond, so we say the force constant is 5 10 to the 5th dyne per centimeter. Okay, so then we use Hooke's law. So nu bar naught is 1/2 times pi times 3 × 10⁻⁻⁻, right? Speed of light in centimeter per second. So you add 200 here, or sorry, 100 times 100. And then we have the square root of k 10⁵ over, okay, so reduced mass. Sorry, I didn't calculate that explicitly here. Mu is 1.54 10⁻⁻24 grams. Okay, 1.55 10⁻⁻24. So this is 3021 centimeter minus 1. So that should be, if I measure a carbon-hydrogen bond, stretch bond right here, it should appear at this wave number, 3021. Okay, we'll see later that that really depends a bit on the environment, but okay. So let's look. Going to cheat again, sorry. There you go. So this is for the different bond types. I'll give you a couple minutes to copy this if you want. So the different bond types, just using this calculation, right? So we use Hooke's law. We know the masses of all these atoms, right? This is just in the periodic table. And we know, sorry, I changed this to K later. Right, so this is K. This is corrected in the notes. Okay, so we have the force constants, and so we can calculate, these are the calculated values using Hooke's law, right? And these are the observed experimental values, right? These are experimental. So you can see that this calculation we're doing with Hooke's law is like not terribly accurate. You know, if you look here, 1113, and the reality is here, right? So you see that in many cases, the reality is quite different from the calculated values. Well, often it's somewhere in between, but does not need to be. Depends on the environment. Okay, so it's not very accurate. And it's because we are not considering that this carbon-hydrogen or carbon-oxygen bond is attached to other atoms in the molecule. Okay, we'll get back to what that means later. But first, we're going to look at a small thing which is important, and that's the effect of deuteration. So we replace a hydrogen with a deuterium. Right, this is often done. You'll see that people use this in NMR, people use it in mass spectrometry, people use it in infrared. Because what is the big change when you go from hydrogen to deuterium? The mass. It's like double the mass. So changing from hydrogen to deuterium is actually a really large change in the mass. If you look at other isotopes, so in one of the next classes, when we look at mass spectrometry, we're going to talk about isotopes, right? Many elements have different isotopes. Carbon has carbon 12, carbon 13, carbon 14. And hydrogen, you have deuterium and you have tritium. Okay, that's very rare, but it exists. So when you deuterate things, it has a large effect on the vibration. And so we'll see what that does. So if you consider the reduced mass of carbon and hydrogen, right? It's the mass of carbon times the mass of hydrogen in grams over the sum, right? But now if you compare the weight of carbon and hydrogen, hydrogen is almost nothing compared to carbon. So here at the bottom, this mass is almost, small, is very almost zero compared to the mass of carbon. So we can ignore this on this sum, which makes it approximately this, right? Because carbon is much heavier than hydrogen. This is just a mathematical, approximation. So if we now deuterate this thing, so we go carbon deuterium instead of carbon hydrogen, we can use the same approximation, and we say, okay, reduced mass is roughly this, right? So if I now compare the reduced masses, right, I have mc times md over mc times mh times mc over mc, right? So this is 1, right? And this is also 1. So I have mass of deuterium over mass of carbon, and that's 2 a mu over 1 a mu, right? So that's 2. Okay, so that's what I just said, right? So the mass of deuterium versus hydrogen is a factor 2. So if you put the reduced masses, it's also a factor 2 in this case. Mistakes today. Okay, so if we look at the wave number for carbon deuterium, it should be square root of 1 over 2 times that of carbon hydrogen. So what does that mean? So if you deuterate a compound, and the wave number is not changing by square root of half, that means that the vibration is more complex. Okay, we'll see what that means, more complex. But so if you have a very simple vibration, when you deuterate, for example, this carbon hydrogen bond, then the wave number will shift by square root of 1 over 2 in the most simple case. And so this is used to identify vibration. So if you take the IR spectrum, you suspect, oh, this is this carbon hydrogen bond. To prove it, you can deuterate that, that compound and then measure it again and compare. Okay, so that's understanding infrared vibrations from classical mechanics. Of course, we also have the lovely other thing, which is called quantum mechanics. So understanding infrared from a quantum mechanics viewpoint. Okay, so some statements about quantum mechanics. So in quantum mechanics, energy and momentum, including angular momentum, are restricted to discrete values. Oops. That means they are quantized, right? Like in UV, you have these discrete levels of energies. This is quantum mechanics. In classical mechanics, you only have one. So for a diatom is just a molecule with two atoms, right? You can write the Hamiltonian. I guess you have a class on quantum mechanics sometime. You already had quantum mechanics? Yes, it's this abracadabra stuff with things. Sorry, I don't want to insult anyone, but for me, it's just very difficult. Okay, so we're going to write the Hamiltonian, and we're just going to look at what these different terms are. Okay, so N stands for nucleus, and E stands for electrons. Okay, and so this Hamiltonian, this corresponds to the kinetic and potential energy of this compound. Okay, so these first two terms are kinetic energy operators. Okay, so that of the nucleus and that of the electrons. And then these three are potential energy operators. Okay, so as you probably know, solving this Hamiltonian is incredibly difficult, right? Because, you know, if you consider all the interactions between the nucleus, different nuclei, electrons, etc., it becomes incredibly costly to calculate that thing. Right, so that's the problem. That solving the Hamiltonian is difficult because, the coordinates of the electrons are not separable from those of the nuclei. So that's this VEN term, right? That's the combination of the interaction between electrons and nuclei. Okay, so there is a partial solution. And that's the Born-Oppenheimer approximation. So what does that say? It says that the wave functions of nuclei and electrons can be treated separately. Okay, and this is because nuclear motion is much slower than electrons. So on the time scale of the electrons moving, the nuclei kind of don't do anything. It's a bit similar to this Frank-Codon principle, where the nuclei were also static compared to the time scale of, for example, photon absorption. So this is kind of similar spirit to that. And the result is that this Hamiltonian, let's write it again. VE plus VEN plus VNN. Okay, so the Born-Oppenheimer approximation basically says, okay, this kinetic energy of the nucleus is 0 because it's not moving on the time scale that we're interested in, and also this term is constant. It's not zero, but it's constant. So from a Hamiltonian, you can calculate energies using the Schrödinger equation. And we're going to use the time independent version. So that's the Hamiltonian like this is energy like this. Okay, where E is the energy of the system. Okay. And then if you do a lot of mathematics, which we're not going to do, you can isolate only the vibrational energy, which is E vibration equals. And now it gets confusing because it's again a V type thing. Okay, so here we're still, this is the wave number, right? And this thing here, this is the vibrational quantum number. And so it can be 0, 1, 2, 3, 4, whatever, right? It's an integer whole number that can be any value between 0 and infinity. So what does this mean, right? That there are discrete vibrational energies. Okay. And we can now substitute that into Hooke's law, which is kind of strange because you're putting the quantum mechanical vibrational energy into a classical mechanical equation. But that's what people do. So we're going to do it. E vibration is V plus half times Planck over 2 pi. So all these things are the same, right? So K is still the force constant, mu is the reduced mass, H is Planck constant, this is just 2 times pi, and this is this vibrational quantum number that we are putting in here. Okay, so this, let's call it the quantum Hooke's law. And so the derivation of these energies comes from a model that's called the quantum oscillator. Okay. So this, you have the classical mechanics oscillator that gives you, your vibrational energy. You have the quantum oscillator, and there are other ones because again, as you know probably that in quantum mechanics they can solve the Schrödinger equation for dihydrogen, but for anything larger than that it becomes problematic. So we're going to continue in comparing these different ways of describing the vibrations. And okay, again, I'm going to cheat. Yes, sorry. I have to cheat because otherwise it takes too long. So why am I cheating? Because we're going to compare, this is the same thing that I drew above, right? So this is the vibrational energy from classical mechanics, right? Newtonian mechanics. And remember, we had only one vibrational energy, which was split up. Remember, in this potential, we can go back, right? All the way here. This is the same graph, right? So we have kinetic energy, we have potential energy, and together they gave a constant vibrational energy, right? This is from classical mechanics. So from quantum mechanics, we saw the energy of this quantum oscillator. And so what I draw here, it's the same. So all these graphs are the same, right? It's vibrational energy versus internuclear distance, right? It's all the same. So this quantum oscillator is a slightly better model to describe vibrations, because why? You have different vibrational levels, right? So I have here this ground state, let's say, this is the lowest vibrational state, which is the same as the classical one, but I can have higher frequencies as well. And so here you see a kind of drawing of the wave function, right? So the wave function, the ground state is a single vibration, but you can have overtones, right? Just like in musical instruments, you know, you have a violin or something, you can have overtones on vibrations, on strings, that gives you music. But you can also have overtones on vibrations of, you know, between atoms. And so these vibrational numbers, these are the same ones when we were drawing the electronic states. These are these smaller states that are on top of the electronic states. So you have the electronic states, those are the largest ones. And then you have vibrational levels on top of that. And then in between, you have rotational levels, which we will maybe come to later. Okay, so this quantum oscillator already has different energy levels. But you see that there's this whole number, right? So this is this V that is here. So if we're in the lowest state, V is 0, then so the energy 0 would be half times h wave number, right? And if I'm in the first vibrational level, it would be 1.5 h nu bar, and the second one would be 2.5 h nu bar, right? So it's quantized, there's different energy levels, whereas in the classical model, there's only one vibration. Okay, the quantum oscillator is better, but it has all the energy levels are equally spaced. Okay, so there's a third one, which is again a little bit more accurate, which is called the Morse potential. And so what's different in this Morse potential? Well, several things. The first thing is that you see that in the quantum oscillator, this energy is completely symmetric, right? So compression or extension doesn't matter, it gives you a symmetric response. And the energy levels are equally spaced, right? Whereas in reality, these energy levels, they go closer to each other, right? And at the end, they go, let's say, infinitely close to each other. And of course, if you stretch a bond more than a certain distance, you will dissociate the two atoms, right? So bonds can break eventually. Now, whereas in the quantum oscillator, the bond never breaks. It just always gets higher in energy. So the first thing is that we give room to dissociation. We see that there's a little bit of asymmetry on this side, right? So this, it's not like perfectly symmetric like the quantum oscillator. And these energy levels, they become increasingly close to each other. So if we compare these models, Okay, then towards Morse, it will be more accurate. Oops, well, it's ugly, but so this is more accurate. And this will be less accurate. Okay. But in any case, we know that there are multiple levels, and we want to know which of these levels are occupied. Okay. So which vibrational levels are occupied? And we talked about this in the first class. You can use the Boltzmann distribution. So in the first class, we were trying to see if electronic transitions were probable or improbable based on the Boltzmann distribution. We can do the same thing for vibrational levels. So let's say N1 is the number of molecules in state V is 1. So in the first vibrational level, right, this one. And we compare that to the number of molecules in V equals 0. Right? So that is same as we saw before. It's e to the power minus delta E, the difference in energy between those levels, times Boltzmann constant times temperature. Right? So this is energy difference in joule. And so we have delta E is the energy of this first vibrational level minus the energy of the lowest vibrational level. This is, of course, temperature in Kelvin. And this is the Boltzmann constant. Constant. And that's joule per Kelvin. Okay. So as we calculated before, for this carbon hydrogen stretch vibration, the wave number was 3021 centimeter minus 1. So delta E is hc times the wave number. So this was where the C went. So if you want energy, you have to get the C to the other side. Okay, so let's fill this in. So we have Planck, 6.63 10 to the minus 34 times speed of light. Wait, this should be 10 to the 10th. Okay, now I'm not oh no, this is again, so this is in SI units. Sorry to confuse you. Again, units is everything. So we have to convert centimeters to meters. So we multiply by 100. Okay, and then we get 6.0 10 to the minus 20 joule. Okay, great. So let's fill this into this Boltzmann equation. So N1 over N0 is e to the minus the energy, 6.0 10 to the minus 20 over Boltzmann, 38 10 to the minus 23 times room temperature in Kelvin, 298, is 4.5 10 to the minus 7. So what does this mean? The ratio of N1 over N0 is 4 to the 10 to the minus 7. So very, very small number. What does it mean? It means that the number of molecules in this higher vibrational state compared to the lower vibrational state is incredibly small, right? So there's very few molecules with higher vibrational levels. So at room temperature, only if you convert this to percentage, 0.00045% is in. So it's the same as for electronic states. For electronic states, we did this in class 1, and we saw that again, there was like an incredibly low number. The probability to be in the first excited state at room temperature is incredibly small. And the same holds for vibrational levels. Okay, so this means that at room temperature, only the lowest vibrational level, so it's V0, is occupied. Okay. So this was a very long story just to talk about one single vibration. Now, if we go to molecules, of course, we have more than one vibration. And what do? They couple. So we're going to call them coupled vibrations. Okay, so we have now more than 2 different atoms. Okay, so let's look at a simple molecule, CO2, right? CO2 is everywhere in the air, too much actually. And we can now imagine how these bonds can move, right? So let me just, I'm going to use this later. Okay, so let's imagine that the central carbon, it stays in the same spot, but this right carbonyl will become longer. Okay, and the left one as well. So I have a displacement of the oxygens. Okay. And so this is called a symmetrical stretch. So if we put some delta plus and delta minus here, right? So there's a dipole moment. But do you think this will be visible in infrared? No, exactly. Because when you change this thing symmetrically, the dipole moment overall doesn't change. So because there's no change in dipole moment, this one is not visible. So this will be inactive. Okay, so you don't see it in infrared. If we now look at the same stretch, but asymmetrical, right? So, okay, didn't draw this very well, but this one moved to the left, and this one also moved to the left, right? So they both move to this side. So it's still stretching, but it's asymmetrical. Stretch. This one is active. Okay, so this vibration does change the dipole moment. Oops. Okay, and so in experiments, this CO2 asymmetrical stretch is at 2350 centimeters minus 1. Okay, and we'll see a bit later that actually a normal carbonyl, so normally this stretch is around 1715 centimeters minus 1. And that's because these two carbonyls, they can couple and they can change, they can amplify the vibration. We'll get back to that. Okay, so if you look at an entire molecule and you want to know how many vibrations do you expect, and so that depends on what's called the degree of freedoms. Oh, freedom. So degree of freedom, what is that? Okay, so let's take the example of CO2, right? So it's a linear molecule. And so if we draw, let's just draw it as sticks and balls. Okay, so we have this thing. And now you have to think, okay, what are degrees of freedom? It's how you can move, right? So if I have a point, I can move it up or down, right? Along this, let's say, y-axis. I can move it left and right, which would be x-axis, or I can move it in the plane or out of the plane, which would be the z-axis. So okay, let's draw that. So x, y, and then z would be, let's say, in the plane of the board. And so translation is if all these things move in the same direction, right? So if I move all the three atoms up at the same time, the whole molecule translates up. Okay. And this, of course, can happen in all three directions, right? So if I move all of them left at the same time, the whole molecule moves left. If I move them all into the board, you know this notation, right? So an X is if something is going into the board, and a dot is if something is coming out of the board, you know, like an arrow. So that's translation. Okay, what else can molecules do? They can rotate. All right, so if I take the molecule and let's say it can rotate in the XY plane. It can rotate in the XZ plane. But a linear molecule, when you rotate it around the x-axis, it actually doesn't change. So this one, for a linear molecule, you cannot rotate it in the other direction. It doesn't change anything. Okay. So that's translation, rotation, and vibration. So for vibration, it's all of, it's 3 times n, right? 3 times the number of molecules. Sorry, each atom can move. So it would be 3 times n minus the number of rotations and translations. So for linear, would be -5. So okay, let's summarize that. So we have the degrees of freedom for a linear molecule or for a nonlinear molecule. Okay, so we have translation, 3 degrees of freedom. For nonlinear, also 3, because that's just up, left, or in the board. We have rotation. So for linear, we saw it's 2, because this one here doesn't change anything, right? But if you have a nonlinear molecule, you have also 3 degrees of freedom in rotation. So for vibration, the total always has to be 3 times n, right? 3 times the number of atoms. And so vibration is the total minus translation minus rotation. Okay, so it's 3n minus 5 and 3n minus 6. Okay. So let's look at some of these more complicated vibrations. I'm going to cheat a little bit. Okay. So let's say we look at the molecule which has 2 hydrogens and 2 heteroatoms. Let's say chlorines or bromines or something like that. Okay, so we can distinguish different symmetries. So we can have symmetric movements or anti-symmetric. Anti-symmetric. Okay, so let's first look at what happens if we stretch both these bonds at the same time outward, right? So like this. So that we would call it symmetric stretch. And just for information, I'll put the wave number, right? But this can also happen like this, right? So one can contract and the other one can go out. So this is, okay, this is hard gymnastics for me, but let's say like this, right? So it's anti-symmetric. Anti-symmetric. Next class, I'll show you some movies of, you know, how these things move. Oops, sorry. Okay, so these are radial motions, and these are stretching. So stretching vibrations always happen at larger wave numbers than bending. Okay, so let's look at bending. So we'll do in-plane bending first. Okay, there you go. Okay, so this motion is if both move inward. So this is scissoring like this. Okay. Both the heteroatoms are doing this. it's symmetric, right? So it's in the symmetric column. Oops, so it would be soaring at this wave number. And the other one, it's similar, it's rocking. So it's with two arms at the same time. Okay, so rocking. 720 centimeter minus 1. Okay, we have some more funny names coming up. So 2 more. So this would be out of plane, bending. Okay. So if they both move to the front and the back at the same time, that's called wagging. Okay. Wagging. Around 1350 to 1150 centimeters minus 1. And if you have one that moves to the front and one to the back, like this, it's twisting, right? Twisting. Same wave numbers, around 50. Okay. Put a line here. Okay, so if you have, so the first thing to notice is that this stretching vibrations, they happen at much larger wave numbers than bending, right? You're here at a much lower wave number. So if you have larger molecules, let's look at, for example, this compound. And we look at this proton, we can have this proton can, bend out of plane. Or you can have in-plane bending. Okay, so this will happen at different frequencies. So in infrared, you can sometimes distinguish all these different vibrations. That also means, you can imagine for one molecule, you have a gigantic number of vibrations, and these smaller ones, let's say all the carbon, hydrogen ones, they can happen in this fingerprint regime where it's very crowded with peaks, whereas some functional groups, let's say CO stretch, would be very characteristic somewhere in the IR. So requirements. Okay, so these are kind of the rules to know what's going to happen. So for vibrations to couple with each other, they must be of the same symmetry, right? So stretching with stretching, for example, that can have a coupling. For example, if we go back to the example I gave before, if we look at a normal carbonyl stretch, oops, stretch T here, it would be at 1715 centimeter minus 1. But in CO2, because I have coupling between one carbonyl and a second carbonyl, right? So I have two coupled carbonyl stretch. And therefore that wave number is shifting much higher, 2350 centimeter, right? So coupling often leads to a shift of the vibration wave number, which is how you can detect that things are coupled. Okay, so for stretching, vibrations. You can have strong coupling. When there's a common atom between them. Okay, so in CO2, right, I have carbon. So the carbon atom connects the two carbonyl stretch vibrations. Okay, so same symmetry and a common atom. But still, you can still think of these things as springs, right? So if you have two springs and there's one in the middle, it's going to couple in some way. Okay, so the third one is, and then we're almost finished, I think, that the interaction is greatest when the coupled groups absorb individually near the same frequency. Again, we'll come back to that a little bit in the next class. So again, for CO2, these are identical carbonyls, right? So they can strongly couple because they share an atom in between them and they have the same frequency. So the coupling will be strong. Okay, this is just, this is quite simple to understand, but a little bit more complicated is you can have coupling between bending and stretching. Okay, so bending and stretching, they can couple if they are part of the same triangle. And so you can think of it in this way. So if I have, let's say, a molecule like this with 3 atoms, A, B, and C, then bending will change the angle, right? So let's say I have in-plane bending like this or here. So the molecule is changing alpha. You can imagine that if I look at stretching, which would be, a change in length of AB or BC, because it's forming part of the same triangle, that this bending then couples with the stretching. So but they have to be close, right? They have to be in the same triangle. So you cannot have these interactions over longer distances. Okay, so bending vibrations can couple when they share a common bond. Okay, this is more trivial to understand. And the last one, coupling is negligible. So very small when groups are separated by one or more carbon atoms, and and the vibrations are mutually perpendicular. Okay, last thing. So these are the requirements for coupling. Of course, there can be some other effects. And the first one is hydrogen bonding. Right, so hydrogen bonding in general can be intramolecular. That means within the molecule. So for example, I have a compound like this, and I have a carbonyl, and I have next to it an alcohol. Then I can have a hydrogen bond that forms here. Right? And so this hydrogen bond, this one, will change the stretching vibration, for example. And so the change you expect, oops, that's wrong, of course. The change, the delta in the wave number is roughly 10 to 300 centimeter minus 1. So if you see a carbonyl and it's like 300 centimeter minus 1 from its normal position in another compound, let's say you have, instead of a hydroxy, you have a methyl group there, or nothing, then you will observe probably a shift in this carbonyl stretch vibration. Okay, so that's indicative of hydrogen bonding, intramolecular or intermolecular. Right, so for example, you have a compound and you have a carbonyl here. You can form a hydrogen bond between molecules, right? Again, you can expect a shift 15 to 500 centimeter minus 1. So again, in general, so you can have hydrogen bond donors. Right? And okay, many compounds can both be a donor and an acceptor. For example, water can be a hydrogen bond donor, it can be a hydrogen bond acceptor. But let's just draw a couple. Right. Alcohols. Okay, so an acid, alcohol, they can donate in the hydrogen bonds, or you can have hydrogen bond acceptors, which can be a very good one is the carbonyl. So carbonyls are only acceptors, they cannot be donors. The lone pair of a nitrogen or lone pair of an oxygen, they can be acceptors. So if you have hydrogen bonding, that is definitely going to shift your infrared vibrations. And also, like in basically all spectroscopy, you have solvent effects. Right? So the n, pi, and pi star orbitals, they are stabilized to different extent. in polar solvents. And so especially the N2 pi star is most affected. And this will blue shift. Right, we saw that in UV class, so that means to higher energy. In a polar solvent. So for example, acetonitrile. If we look at the frequencies, so solvent, and this is the wave number of the nitrile vibration. Oops. Then in hexane, it's very apolar, right? This is 2260. Nitromethane, a bit more polar, but not very polar, 61. Ethanol, 64. Methanol, 2266. So there's definitely a shift, right? So this is more, this is polar, and this is apolar. So there's definitely a shift when you change the solvent polarity, but the shifts are not as large as when you do hydrogen bonding, for example, or when you have coupling between vibrations. Okay, I think we had enough for one day. Any questions? Okay, see you in the next class. Thank you.